Military drones, or unmanned aerial vehicles, UAVs, have become pivotal in modern warfare, executing a range of tasks from surveillance and reconnaissance to direct combat operations. This comprehensive examination delves into the intricate engineering behind these drones, with a focus on concepts essential for aerospace and mechanical engineers. Military drones come in various configurations, primarily classified into fixed-wing, rotary-wing, and hybrid types. Fixed-wing drones, resembling traditional airplanes, are typically utilized for long-range missions due to their efficient aerodynamics, allowing for extended flight times and greater endurance. The design of these drones is optimized for sustained forward flight, making them ideal for tasks requiring coverage over large areas, such as reconnaissance and surveillance. Rotary-wing drones, including quadcopters and helicopters, are characterized by their ability to hover and perform vertical takeoffs and landings. This maneuverability makes them suitable for a variety of operations, such as close-range reconnaissance, search and rescue missions, and targeted strikes. The rotary wing design provides significant advantages in confined or rugged environments where fixed-wing drones might struggle. Hybrid drones combine elements of both fixed-wing and rotary-wing designs, offering versatility for a wide range of mission requirements. These drones can take off and land vertically like rotary-wing drones, but transition to fixed-wing flight for greater efficiency over longer distances. This hybrid approach allows for flexibility in operational planning and execution. Understanding the aerodynamics and design of drones is essential for optimizing their performance. Key aerodynamic principles, such as lift and drag, are fundamental. Lift is generated by the drone's wings or rotors, enabling it to ascend and remain airborne. In fixed-wing drones, lift is primarily produced by the shape of the wings, which are designed to create a pressure difference between the upper and lower surfaces. The Bernoulli principle plays a crucial role here, where faster airflow over the curved upper surface reduces pressure, thus generating lift. Drag, the resistance encountered as the drone moves through the air, is a critical factor affecting efficiency and speed. Engineers strive to minimize drag through streamlined designs, careful selection of airfoils, and smooth surfaces. In rotary-wing drones, the rotating blades create lift by varying the angle of attack as they spin, a process managed by sophisticated control systems to maintain stability and control. Wing design in fixed-wing drones involves careful consideration of factors such as shape, aspect ratio, and airfoil selection. A higher aspect ratio, which is the ratio of wingspan to wing chord, generally improves aerodynamic efficiency, reducing induced drag. However, it must be balanced with structural considerations and mission requirements. Airfoils, the cross-sectional shapes of the wings, are designed to optimize lift-to-drag ratios for different flight conditions. In rotary-wing drones, propeller and rotor design are paramount. The size, shape, and pitch of the propellers directly impact performance. For instance, larger propellers with a lower pitch are more efficient at lower speeds, providing greater lift and stability. Engineers must consider factors such as thrust-to-weight ratio, rotor blade stiffness, and vibration damping to ensure optimal performance and reliability. The materials and structures used in drone construction are pivotal in achieving a balance of strength, weight, and durability. Lightweight materials such as carbon fiber composites and lightweight metals like aluminum and titanium are commonly used. These materials offer high strength-to-weight ratios, enhancing performance and endurance. Carbon fiber composites are particularly advantageous due to their stiffness and resistance to fatigue and corrosion. Ensuring structural integrity is crucial, as drones must withstand various forces during flight, including aerodynamic loads, vibrations, and impacts. Engineers employ advanced modeling and simulation techniques to predict and mitigate potential structural issues. Finite element analysis, FEA, is often used to optimize structural components, ensuring they can handle the stresses encountered during operation while minimizing weight. Propulsion systems in drones vary but are a key aspect of their engineering. Electric motors, particularly brushless DC motors, are preferred for their efficiency, reliability, and low maintenance requirements. These motors provide high torque and power-to-weight ratios, making them ideal for UAV applications. The selection of electric motors involves considerations such as power output, efficiency, thermal management, and integration with electronic speed controllers, ESCs. The power supply, typically lithium polymer, LiPo, or lithium-ion batteries, plays a significant role in determining the drone's endurance and performance. LiPo batteries are favored for their high energy density and ability to deliver high discharge rates, essential for powering motors and onboard electronics. Engineers must carefully manage battery weight, capacity, and thermal characteristics to optimize flight times and reliability. Larger drones may use fuel-based propulsion systems, which require careful engineering to manage. These systems offer higher energy density compared to batteries, enabling longer flight durations and heavier payloads. However, they introduce complexities such as fuel management, combustion efficiency, and emissions control. Hybrid propulsion systems, combining electric and fuel-based power sources, are also being explored to enhance performance and operational flexibility. Navigation and control systems are vital for the precise operation of drones. GPS and inertial navigation systems, INS, are used for navigation and positioning, providing accurate location data and enabling autonomous flight paths. GPS relies on satellite signals to determine the drone's position, while INS uses accelerometers and gyroscopes to track motion and orientation. Integrating these systems ensures reliable navigation even in challenging environments. Flight control systems, managed by onboard computers and sensors, maintain stable flight. Gyroscopes and accelerometers detect changes in orientation and movement, allowing the control system to make real-time adjustments to the drone's attitude and trajectory. Advanced algorithms, including proportional integral derivative (PID) controllers, are used to ensure smooth and responsive control. Autonomous systems, incorporating artificial intelligence, AI, and machine learning, are increasingly important for future drone technology. AI enables drones to perform complex tasks with minimal human intervention, such as object recognition, path planning, and adaptive control. Machine learning algorithms can enhance the drone's capabilities by learning from data and improving performance over time. Drones are designed to carry various payloads, including cameras, sensors, and weapons. The integration of these payloads involves complex engineering to ensure optimal performance and functionality. Engineers must consider factors such as weight distribution, power requirements, data transmission, and environmental protection. Payload integration often involves modular designs, allowing for quick and flexible reconfiguration for different missions. Weapon systems, in particular, present unique challenges in terms of integration and deployment. Engineers must ensure that the drone can safely carry, aim, and discharge weapons without compromising stability or control. This involves careful consideration of factors such as recoil management, targeting accuracy, and safety protocols. Thermodynamics and heat management are critical for the longevity and reliability of drones. Effective heat dissipation methods, including passive and active cooling systems, are necessary to manage the heat generated by electronic components and propulsion systems. Passive cooling involves heat sinks and thermal management materials, while active cooling may include fans or liquid cooling systems. Engineers must balance cooling efficiency with weight and power consumption to ensure optimal performance. Communication systems in drones involve advanced technologies for real-time data transmission and secure signal processing. Reliable communication links between the drone and ground control stations are essential for command and control, telemetry, and video feeds. Engineers use techniques such as frequency hopping, encryption, and error correction to ensure secure and robust communication, even in contested environments. Future trends in drone engineering include advancements in artificial intelligence, new materials and manufacturing techniques, and enhanced autonomy. AI and machine learning are expected to play an increasingly significant role in drone operations, enabling more sophisticated autonomous capabilities. Innovations in materials science, such as advanced composites and nanomaterials, promise to further enhance the performance and durability of drones. Enhanced autonomy, including swarm technology, will enable coordinated operations of multiple drones, expanding their applications and effectiveness in military operations. By understanding these engineering principles, aerospace and mechanical engineers can contribute to the development of more advanced and capable military drones, ensuring they meet the evolving needs of modern warfare.